let me welcome you all to this 13th webinar of the graduate program in physics of the Federal University of Pará in Amazônia, Brazil. I ask you to kindly leave your audio and video sources turned off, except for the moment you're going to speak. Questions will be allowed after the webinar, unless otherwise requested by the speaker. The questions can be made using the chat. Today, we're honored for the opportunity to hear from Professor Rosa Valentí, who has never visited our graduate program in Amazonia, and therefore this occasion is special for us. Rosa Valentí is Professor of Theoretical Physics at the Goethe Universität in Frankfurt, Germany. She received her PhD degree in theoretical physics at the University of Barcelona in Spain. Before joining Frankfurt, she was postdoctoral Fulbright Fellow at the University of Florida at Gainesville in the United States and habilitation researcher at the University of Dortmund in Germany and Heisenberg Fellow at the University of Saarland, also in Germany. From 2009 to 2012, she was Vice President of the Goethe Universität Frankfurt, and since 2016, she is an American Physical Society Fellow. Her field of research is computational solid state with a focus on microscopic modeling of correlated materials such as unconventional superconductors, frustrated magnets, and systems with topologically non-trivial states via a combination of first principles-based methods and many-body numerical techniques. Among the distinctions received by Professor Valentí, I can mention the Michael and Bizerka Baum Prize from the Goethe Universität in Frankfurt, which she received in 2009. Well, we are here today to listen to Professor Valentí, so that I won't take your time further with this introduction. Professor Valentí, thank you once again very much for having accepted our invitation, and the audience is yours.
Thank you very much for this very kind introduction, and it's a pleasure for me to be virtually in Brazil. I would rather like to be there in person, but we all know because of the present situation, but at least we do it virtually. And today I'm going to talk about quantum materials. And in the next 45 minutes, I would try to convince you about the importance of quantum materials design on the computer. And I will discuss the challenges and the opportunities that we face in this field of research. So here in this picture, what I'm showing is an engineered heterostructure of two very much discussed nowadays materials, and I will present these along the way, what is interesting about this type of material. So I have divided this talk in three parts. In the first part, I would like to introduce the concept of a quantum material, and especially what we call correlated materials, and also describe and motivate why they are special and why we would like to have more of those. Then in the second part, I will present some strategies that we have been following in recent years in order to predict such quantum materials with unconventional properties. And in the third part, I will present some examples of these predictions, their experimental realization. And if I have time, I will also discuss with you some predictions that never worked and tell you why they never work. So let me start with the definition of a quantum material. So if we think about a piece of iron, this is a quantum material if we consider the description of this system at the microscopic level. So it means at length scales, which are 10 to the minus 8 meters. At these length scales, what we have is a system of interacting electrons with the ions that, in this case, they form a crystalline lattice. And the electrons have a charge, have a spin. They occupy various different orbital states, interact among them, and interact with the lattice. And it is, in fact, this simultaneous action of all these degrees of freedom what results in distinct phases of matter. And here I would like to quote this work from Phil Anderson, who recently, unfortunately, passed away, the work on more is different, and the concept of emergence, the fact that due to the collective effect of various different individual degrees of freedom, one can obtain phases that you cannot predict only by knowing the constituents. And in fact, this concept of emergence, which results from a collective effect, is not only seen in quantum physics, but we also have it in all other situations. So let me show you, for instance, the case of a flock of birds. So you know that the birds, when they fly in the sky, they form very special patterns that you could never predict by just counting one bird, two birds, three birds. So it's in fact a consequence of the effect of the collective effect of these birds. So we describe emergence as a behavior which is not foreseeable from the knowledge of the constituents alone. And this is the case also in quantum materials. So what I want to do in the next slides is to try to understand which are the interactions between these different constituents that give rise then to different phases of matter. Some of them, we call them, in fact, exotic phases of matter because they are happening rarely. And these are the ones, in fact, that we would like to have. So here in this slide, what I tried to do is to basically define the basic interactions that are important when we are describing quantum materials. And let me just show you what is the notation here. So these circles in the middle, what I want to describe is the strength of the interaction from little strength with very dominant strength, from inwards now going outwards. And let me just show that there are four basic interactions that we consider. One, of course, is the kinetic energy of our electrons. So for the moment, I'm going to state in the system of electrons. So the electrons have a kinetic energy that I can describe mathematically in second quantization, basically by a hopping T parameter and then creation and annihilation operators from one side to the next. And this is in fact a one particle property. So therefore, I have put it here in this side of the diagram. There is another important one particle interaction, which is the spin orbital coupling. So the electrons have a velocity. When this velocity is very high, you know that we have to start considering relativistic effects. So the fact that at these high velocities, there is a coupling of the spin of the electron with the orbital momentum. And this is what it produces relativistic effects. And we have to then take into account this effect in our description. It happens in the case, for instance, of what we call F electrons or 4D or 5D electrons, where this interaction is going to be important. And again, this is a single particle interaction. Let me go now to the multi-particle interactions, which are what we call our headache when we want to describe materials, and at the same time are the ones also that produce very many interesting phases in matter. So one important interaction is the Coulomb repulsion. So the Coulomb repulsion, due to the fact that the electrons have a charge, you know that there is a strong repulsion between the electrons, and a very simplistic way of representing this Coulomb repulsion effect is by this term, which is an on-site U. This is the energy that I have to pay in order to put two electrons on the same side. And if I put them on the same side, of course, it will be one up and one down. Otherwise, due to Pauli principle, they would never be on the same side. So this is our Coulomb repulsion. And it's a multi-particle interaction because it's a two-body interaction in a many-body problem of our interacting electrons. And there is one more interaction that I want to bring into our description, which is the Hund's coupling. So what is the Hund's coupling? So the Hund's coupling is what we call an intra-side interorbital exchange interaction That means we have, for instance, iron, where on one iron side, I may have many orbital states that our electrons can occupy. So therefore, there is then, due to the spin of the electrons, there is an exchange in between these orbitals, and this exchange, in fact, follows what we call the Hund's rule. So this parallel setting of the electron spins is favored with respect to this antiparallel. So there is also an energy that we have to consider in the description of these multi-orbital systems. So now, by just taking these four interactions, I could, in principle, categorize the different systems that I'm going to describe in the next slides, depending on how strong are these four interactions for the system. And here is I have represented that depending on the strength of the interaction. So let me go through these examples just to now motivate, especially systems with strong Coulomb repulsion. So systems where we are going to see this arrow very much going to the outside circles. So one class of strongly correlated systems, which is in fact very famous because of one special property, because this class of materials show superconductivity at very high transition temperatures. These are the so-called high TC cuprate-based superconductors. So these materials, this superconductivity property was discovered in 1986. So I'm talking about a class of materials that have been discovered more than 30 years ago. And let me tell you what is special about these materials. So the structure of these materials is copper oxide planes, as you see here, that they are basically stacked along the Z direction, and between these copper oxide planes, we have cations, for instance, in this case, lanthanum. And when we are in the case of what we call the stoichiometric materials, so X is equal to 0, lanthanum, copper, or 4, in this case, the system behaves, it's an insulator, and shows long-range order. So it's an antiferromagnetic insulator, but it's what we call a Mott insulator, because the reason why the system is insulator, it's due to the strong Coulomb repulsion that the copper d electrons feel. And because of this strong Coulomb repulsion, the state that the system shows is a very localized state, so it becomes an insulator. And what is interesting is that when we doped the system, for instance, here by substituting lanthanum cation by another cation, where the effect of this substitution is to give or extract, in this case, we're going to extract electrons from these copper planes, that means that we are going to allow free states for electrons starting to move. And when this is being done chemically, what one observes is that the systems become superconductors, and superconductors at transition temperatures that have right now, I think we are at about 155 Kelvin, which is really very high for a superconductor. So what is important now is how do we describe these materials? We see that there is a magnetic phase near a superconducting phase, which is going to be important for the description of the properties of this kind of systems. And moreover, there are many other phases in this temperature doping phase diagram that I'm not going to discuss, but they are still nowadays an intensive subject of discussion. So how do we describe now, with these four interactions that I was showing to you, this type of materials? So basically, there are two important terms here. One is the hopping term, and second is this strong Coulomb interaction. And when we consider now the Hamiltonian description in terms of these two terms, this is what we know as the Hubbard model. So the Hubbard model, as you see, it's a very simple model, however, is only exactly solvable in very special cases. And in the case of these materials, there is no exact solution. So when we want to describe this physics, we need to think about approximations to this Hubbard model. And moreover, we need to know how we then relate these parameters, the hopping matrix elements, and this interaction to the real parameters of the system. So this is something that we would like to be able to describe from what we call first principles, and then try to find also materials that show this type of properties, so show this high TC superconductivity. Let me show you two more examples of interesting classes of material where correlations have an important role in the description of their properties. And by the way, just to show you that this description of correlating materials is extremely hard. So when this high TC cuprates were discovered in 1986 by Bernoth and Müller, just the next year, so 1987, they got the Nobel Prize for this discovery. However, we are now more than 30 years after this discovery, and still there is no Nobel Prize for the description of these properties. And the reason for that is because it's very hard to treat this Coulomb repulsion in a many-body. So this two-body interaction in a many-body problem. So the second class of materials I wanted to just show to you are the iron-based superconductors. So in 2008, there was a new class of superconductors coming into the field. Even people have called that as the second age, the second iron age, since this was in fact the first reports of superconductivity in this class of materials came from the lab of Hosono in Japan. And again, as you see, let's first look at the structure. They have a similar structure that, as these cuprates that I just talked about show. So now what we have is planes of iron and arsenic. So the layers are now not the copper oxygen, but iron and arsenic. And they are again separated by some cation species. And if we look at the behavior of the system, so again, I'm doing a phase diagram, temperature as a function of doping. In the parent compounds, these systems are again magnetic. They show a long-range magnetic order. However, the difference between this class of materials and the high TC cuprates is that the parent compounds are not insulators. They are still metallic. So they are metallic. When one then dopes the system or puts the system under pressure, they become superconductors. And the superconductivity, it's also rather large. The highest TC in the bulk systems is right now 55 Kelvin. It's not as surprising as for the high TC cuprates, but it's really high compared to what you expect for what we call a classical superconductor. So classical superconductors are those that are described through electron-phonon coupling, and there the TCs are much lower than this 55. Again, here, what we observe is that there is a magnetic phase near a superconducting phase. So that, again, we have this competition of magnetism and superconductivity. So now if we want to describe these materials, again, through our four interactions, what we would have here is, again, the hopping term of our itinerant electrons. In our case, the itinerant electrons are the iron D electrons. We have Coulomb repulsion. These are 3D electrons, so there is a Coulomb repulsion. But in our case here, we also have an important Hund's coupling term because we are dealing with a multi-orbital sites. So therefore, there is a new interaction entering into the game for the description of these iron-based superconductors. Now, let me go 10 years later, and 10 years later, we have had a very nice discovery of, again, superconductivity in a correlated system, and this is the case of twisted graphene. And now I'm not anymore in the world of bulk systems, as I was in the 2 classes shown to you previously. Now I am in the world of 2D materials. So in fact, in 2010, Bistritz and Alan McDonald, they predicted that if you take 2 layers of graphene and basically you rotate one with respect to the other, then the electronic properties of this twisted set of 2 layers of graphene is going to be very special. So it's going to have at the Fermi level. So as you know, the Fermi level is whatever happens near the Fermi level is what is important for the transport properties of our system and what is important for such properties that I was showing to you, like superconductivity and magnetism. So what happens then when you twist these 2 layers is that the band structure, and band structure, what I'm showing to you is the energy states that you expect in the reciprocal space of K, where K, if you think in a block wave description, so basically this is the reciprocal space description. So these very flat bands of dispersion, it's going to allow for having that the relation between the dispersion, so basically the itinerancy of your electrons, and the Coulomb repulsion, they are going to be of the same order of magnitude. And this is important because it's telling us that we are going to expect that the properties of the system is going to be similar to what we know from the correlated materials that I showed you previously. And in fact, these are the experiments done in the lab from Pablo Jarillo Herrero, and this has been confirmed now by many other labs, where they did, in fact, this experiment of twisting to this, what it's called the magic angle twisting. And here it's shown temperature as a function of carrier density. So the way to change the carrier density in these devices is basically by gating the system. And as you see, what they find as a function of carrier density, if we are in the case where there is a neutral carrier, we have a mod insulator, and by now changing the doping, so the system becomes superconductor. And this was, in fact, it's an impressive discovery that you can have this physics of correlated systems also in these engineered 2D materials. So now let me bring the 4th interaction into the game, which is the spin-orbit coupling. And here, if we now include spin-orbit coupling and we consider systems where all these 4 interactions are playing a role, depending on the strength of the interaction, we can have even more phases into our systems. So here I'm showing basically the Coulomb repulsion as a function of the strength of the spin-orbit coupling. And as you can see, if I go to large Coulomb repulsion, we have these mod insulators like the high-TC cuprates in the parent compounds. But then as a function of lambda, we have a large variety of new phases like spin liquid, axion insulator, vial semimetals, etc., etc. So you see the physics becomes extremely rich. It's just a matter then of knowing how to deal with this description to reach for realistic materials to reach into this realm of phases. So here is where we are now interested in is how can we design correlated materials with such unconventional properties as those that I was showing to you for the materials we know. And we are theorists, so we want to do that on the computer. That's what we know how to do. Of course, very much guided by experiment, but basically we want to see how far we can go with computational simulations to predict this type of phases in systems. So the question is whether we start with. So, of course, what is the dream of a theorist for this type of predictions is the possibility of predicting materials starting from first principles. So that means starting from the basic interactions between electrons and lattice, and from there try to then predict phases like the ones I was showing to you. So of course, we know we have the periodic table of elements to play with. So we could start doing combinatorics of different atoms and try to build out of that different type of bulk materials if I am now interested in bulk materials. But this is extremely ineffective. Let's first settle which are the important equations I should take into account to do these descriptions from first principles. So the important equations, and right now I'm not interested in dynamical properties, and here I even simplified to the case of non-relativistic and Born-Oppenheim approximation. So I'm considering that the lattice is basically static, and we're only interested in the description of the many-body electron system. Already at this level, this becomes an impossible action, in the sense that if we just write the Schrödinger equation, which is what describes, in fact, the energy levels of the systems, and from there you can describe the properties of the systems, you basically would write your Hamiltonian as your kinetic term, your Coulomb attraction with your ions in the crystalline lattice, and the famous electron Coulomb repulsion. And if we consider that we have, let's say, 1 cubic centimeter of a given material, we have 10 to the 23 electrons that are interacting. So we would be having 10 to the 23 coupled equations due to this Coulomb repulsion. And this is impossible to solve, not with our computer and not in the next years. And it's also not necessary to solve these equations. And with here, I want to go to a very important theory that was developed in the last century and has been, in fact, extremely fundamental in order to be able to describe the electronic properties of systems without having to solve these coupled equations of coupled Schrödinger equations. And this is the density functional theory. So the density functional theory is a very nice and simple concept. Walter Kohn got the Nobel Prize in chemistry was one of the Nobel Prize awardees for this theory in 1999. And it is based on the Hohenberg Theorem, which is a very simple theorem that sure, if we have in the audience graduate students, you have probably already seen this theorem, so that the ground state of a system of interacting particles is a functional of the ground state density. So what this theorem is telling us is that you don't need to know the full wave function of your 10 to the 23 electrons to know the properties. In this case, for instance, the ground state energy of your system is enough that we know the ground state density. And this is basically, the ground state density is a function only of 3 coordinates, x, y, and z. However, we don't know how this functional looks like. So the theorem tells us this functional exists, but we don't know how it looks like. So Kohn and Sham, they propose the Kohn-Sham ansatz, which is what makes this theorem, in fact, practicable. And the idea of this ansatz is to replace this interacting many-body problem that you described with this functional with a non-interacting problem where all the many-body effects are in what we call an exchange correlation functional. And all the approximations are done in this exchange correlation functional. This ansatz makes the density functional theory, in fact, practicable, and it has been extremely successful for predicting, in fact, many states of matter since it was proposed. However, I was telling at the beginning that I'm interested in correlating materials. So materials where the Coulomb repulsion is strong. It's not screen, it's strong. And here in the DFT formalism, in the Kohn-Sham ansatz, the approximations are done in this exchange correlation functional. That means they are done precisely in this Coulomb term and in the exchange term. So there are effects that cannot be described by such a theory. And let me show you one of those. For instance, so what the correlation effects are doing to your system. So here what I'm showing is, again, a representation of energy states in the reciprocal space. So if we have a system of non-interacting particles, basically the states will be represented by delta Diracs. So that means that the particles have an energy at a given k, and it has an infinite lifetime. However, if these particles interact, they will start scattering, at least in this representation that I'm using here. They start scattering with each other, and what this can be represented in a Green's function formalism in terms of what we call the self-energy. And what happens then is that the particles have a finite lifetime, and there is a transfer of spectral weight to what we call the lower and the upper Hubbard band. And this, in fact, is influencing the properties of the system. So we need to have methods to describe these effects which are not captured in, for instance, DFT. And just to show you how to include these effects, which are, for instance, in this type of Hubbard models, in the Hubbard model, because you explicitly take into account this Coulomb repulsion, one can describe what I was telling to you, the effect of this transfer of a spectral weight due to the Coulomb repulsion among the particles. So what we do then for our simulations is a combination of DFT with many-body methods. And we call many-body methods the methods that treat this type of models, so that treat correlations effects beyond DFT. And one method that is very, in fact, very useful is a dynamical mean field theory, which basically describes the correlations effect by doing a mean field, a dynamical mean field. So basically by describing your system of interacting d electrons in the picture I'm showing here as one central d electron interacting with a bath. But this interaction contains all the dynamics of the interaction. So that means that this kind of approximation includes all local correlations exactly. So this is, in fact, what we are doing when we're describing these correlated systems is to combine DFT with many-body methods that take into account these correlations effects. So, okay, now we have, in principle, a set of methods how we can deal now with our predictive options. So we go back to our basically what we had, our periodic table, and still the question is, how do we start? Now we know which equations we're going to use, but how do we start now? By doing the combinatorics of different elements in this periodic table. So in fact, the question is ill-posed if I started like that. The question that I should answer is what I'm looking for. So which property would I like to have in the material that I'm going to construct? For instance, if I'm interested in predicting a material that has high TC superconductivity or that shows high TC superconductivity, and this is important, this property is important, for instance, for energy efficiency purposes. So let me see what we learn from the materials that are there about where do we find this high TC superconductivity. So for instance, if we think about the traditional superconductors, like niobium-3 tin or magnesium diboride, in these materials, these electron phonon superconductors, which in fact, magnesium diboride is one of the highest TCs in electron phonon. I think it is about 20K, but it's the highest TC that one can reach with this type of mechanism. So here, this type of traditional superconductors, the search is easy because you see these are stoichiometric materials. So in principle, I could do these combinatorics that I was talking about. However, the materials I showed to you, we manipulate the systems in order to obtain this high TC superconductivity in the copper base or in the iron arsenic base or in this twisted bilayer. We had to either dope the system, put the system under pressure, or start twisting. So this is a much harder search if you want to start from this, basically this periodic table. So I have to think how I deal with that if I want to predict such a property. If I want to, let's say, look for spin liquid phases, and I didn't define to you what it's a spin liquid phases. So this is a very strongly long-range entangled ground state, that is interesting for us because this kind of states have fractionalized excitations, and there have been a lot of proposals of quantum computers built out of these making use of these fractionalized excitations. So these are also other phases that would be interesting for us to investigate. So in order to now answer how we proceed now in our design, we have three different strategies. So one, and this is more based on these high TC superconductors, is to use known correlated materials and then tune them either chemically or by pressure in order to allow them to manifest other properties. A different second strategy is a completely different starting point. So we know that there are models in physics that there are models that maybe have no meaning at all, but we can solve them exactly. And if we can solve them exactly, and with that, I mean that we can basically obtain ground state and excited states, everything in an exact way, then from there, it would be interesting whether we can find a realization of this model in real life. So look for realizations of exactly solvable models. And the third case is basically now thinking of these 2D materials to manipulate the properties of these 2D materials by, in fact, manipulating the dielectric environment. I'm not sure how time I will have for going through them. Let me just start, and Luis, you stop me when you say I have talked too much. So let's see. Let me give you an example of each. So, for instance, to use non-correlated materials by tuning them with pressure. So, with that, I would like to show you an example of straining one of these high TC iron-based superconductors, where, in fact, by doing simulations, we found out that one could have very interesting properties that could even functionalize the system. So let me show you what we have been using for these materials. So this is calcium, potassium, iron 4, arsenic 4. Again, this iron-based superconductor. This is a family member of the iron-based superconductors. The system is paramagnetic. It's a metal paramagnetic. When you go down in temperature, it becomes superconductor at 35 Kelvin. The system, what is interesting is that the structure of the system is tetragonal, and it's what is special about this tetragonal structure is this body centering, so that you see that these planes of iron arsenic basically separated by these cations, potassium and calcium. What I want to put your attention to is that the arsenic here, the arsenic atoms, the electrons of the arsenic atoms that occupy pz orbitals, so basically they are vertical pz orbitals, what we are going to use is the fact that if you press the system, these pz orbitals at a critical pressing, so when you push them together, they are going to bind and form a bonding, a chemical bonding state. And these, as a consequence, what it has is that it collapses. You observe a collapse of your volume due to the formation of this bonding. So what we did, and these were simulations from Vladislav Borisov, basically is to precisely do that, take the system and simulate the effect of strain, uniaxial strain on the system, and investigate what happens to the properties of the system once you apply this strain. So the prediction was that at a certain critical strain, you will have this bonding. You go from this tetragonal to this collapsed tetragonal state. But what is more important, you go from a superconductor to a metal phase, and that this type of effect is reversible. So and here is the experimental realization by Paul Campbell and Seok-Wook Lee, where they did, in fact, this experiment. You strain the system, it's superconductor, it goes you can strain up to 17%, and then it goes the superconductivity is gone. But if you release the strain, it goes back to superconductor. So you got to do this process back and forth. So this is what it's called. It's a super elastic type of effect. And what is interesting about this material is that the super elasticity is much effective. So the recoverable strain is much larger than any of the materials known, like shape memory alloys, up to present. So this was a prediction of superelasticity, where you have a mechanical switch between superconductor and metal in a known material. Let me go now to my second example, which is, let me just start from a different point of view. Let me start with an exactly solvable model. And I want to introduce to you the Kitaev model. This is a beautiful model which was proposed by Alexei Kitaev in 2006. And now I'm going to stay in the world of insulators. So there is no more superconductivity here for the moment. Let me start now with insulators, so spin systems. So Alexei Kitaev proposed the following model. You take, for instance, a honeycomb lattice, and now you define an Ising coupling, nearest neighbor Ising coupling, but this nearest neighbor Ising coupling is bond dependent. So that means if I am in this X bond, the coupling is going to be XX as X. If I am in the Z bond, it's going to be as Z as Z. If I am in the Y bond, it's going to be as Y as Y. Now, and then you basically what you see is that this is a highly frustrating model because you are on this side. So it means that you are going to interact with your neighbors with a different spin component. And since the three spin components don't commute with each other, it means you have a highly frustrated system. So this is a nice model. And what is even nicer is that it can be solved exactly. So one can extract exactly all the properties of this model. And the way that Alexei Kitaev showed how you solve that exactly is by making use of the Majorana fermion representation. So by introducing Majorana fermions that were, in fact, introduced last century by Ettore and Majorana, these are chargeless fermions. So by introducing 4 of these Majorana fermions, this Hamiltonian becomes quadratic. One can solve it exactly, and one can show that the ground state is a spin liquid ground state. So it is this long-range entangled state that doesn't order. So it's a non-ordered state, but it has a long-range entanglement. And what is interesting is that the excitations are gapless Majorana fermions and static gap fluxes. So these are fractionalized excitations that, in fact, what we would have here is what we call emergence of exotic quasi-particles that may be used, especially on the, if you make them non-abelian on an application of magnetic field, may be used for quantum computing. This was, in fact, the proposal of Kitaev. Now, the question is, it's a beautiful physics, but can we find this type of realization of model in a material? And in fact, George Jacqueline and Ginyat Kalulim proposed that this could be, in fact, realized in materials if one considers materials with a strong spin-orbit coupling and some other conditions like having D5 transition metal ions forming in an octahedral environment and forming edge sharing. So there is a recipe to build up this model in a material. And in fact, there are materials that follow this recipe, like this ruthenium trichloride and these iridate materials. Again, you find this honeycomb lattice, and they basically build layers of honeycomb lattices. So now if you look at the spin interactions in this system, what one finds is that indeed the Kitaev interaction is the dominant one, but there are other interactions that are non-zero, and these materials are not spin liquids, so they are, in fact, they order magnetically, and this is due to these extra interactions. So indeed, there are, one calls them candidate Kitaev, but they are not perfect KTF. We don't have with these systems the realization of the spin liquid. How can we do that? So here is where it comes and probably I will, my time is getting a little bit over. Probably I will end then with this example. So how can one now, using this concept of manipulating via doping and strain, manipulate these systems in order to bring them into this region of having these special properties? So here is a suggestion that, in fact, there are now realizations, so experimental realizations of these type of heterostructures, where basically is to build an heterostructure of graphene with one of these candidate KTF materials with alpha ruthenium trichloride. And there are, in fact, now experimental realizations of these heterostructures. And what is interesting about this heterostructure is the following. So here, these experimental realizations, what they find is, first of all, that there is an increase of the conduction in this heterostructure than what you expect for graphene. So that means that there must be a charge transfer between these two layers. And this is the simulations that we did. So Sananda Biswa in Frankfurt did these simulations where basically by using the DFT, what one observes is that what happens are two things. One is that there is a charge transfer from the graphene to the ruthenium trichloride, so that's why the system becomes more conductive, because there are more holes, more charges in the system. And moreover, also we are influencing this ruthenium trichloride in the following way, because there is a strong mismatch between the two layers, the graphene and the ruthenium trichloride. You see the lattice of the graphene and you see the lattice of the ruthenium trichloride. So what happens with putting these two heterostructures together is that there is a tensile strain that is acting on ruthenium trichloride. And this tensile strain basically improves upon the KTF interaction and makes the other interactions, in fact, very small. So we are going into this direction of spin liquid. Moreover, because of this charge transfer, there is charge coming to the system. And what we predict is that if one now would apply a bias voltage, you could even find a P-wave type of superconductivity in this system. So you see, by now making use of these 2D systems and starting to put them on top of the other in different ways, one can obtain emergent phases that were not possible in the single materials. And since I think I am at I'm done with my time. The dielectric engineering was just to a work that we have been doing for these bilayer materials in order to be able to control the correlations in the system by making use of the distance. If this is your bilayer twisted graphene, and here is where the metallic, basically where the metallic plates are put, of course, one can change the dielectric environment by changing the distance of these metallic planes. So here it's distance with respect to the value of the dielectric constant, and this shows how strong is going to be the correlation. So for instance, by putting ourselves here, you see that correlations increase if you separate basically the distance between your bilayer and the metallic layers. And there are very recent experiments in the group of Dmitry Efetov where they indeed find these predictions that by separating the layer, this twisted graphene, from the metallic layer, which here it's graphite, one observes the presence then of correlated insulator, they call that. So there's increasing of the Coulomb repulsion. So you can now manipulate the strength of correlation of the system by playing with the twisting angle and also with the distance to your metallic layers, and ask questions whether superconductivity is in fact competing with this correlated insulating phase, etc., etc. So with that, I come to the end of my talk. This is the summary. I tried to show to you different types of strategies that one can follow in order to obtain new phases in either known materials or new materials, either by doping new materials or by looking for realization of exactly solvable models or by manipulating with the dielectric media. And of course, right now we are also very much into use machine learning methods for two things. One is for improving the effectiveness of many-body methods, and the other one is also for improving also the search of new materials. And I would, last but not least, thank all my collaborators in the work I've been presented in Frankfurt and so everywhere else. And I thank you for your attention. My time is over. Thank you very much.
Okay, Professor Rosa. So first of all, I would like to ask everybody to turn on their microphones and give a big applause in retribution for this very nice seminar that you have given us. Thank you. Okay, so while people prepare their questions, we already have some registrations for questions, but let me give you an outlook of what has been your webinar. So although, I mean, you have the sensation that you're talking to an empty room, but it's far from empty, right? We have dozens of people, more than 60 people listening to you, and from different parts of Brazil, from the north here, Belém, but also from the southern regions of Brazil, like Rio de Janeiro, São Paulo, Minas Gerais, and institutions like CBPF in Rio de Janeiro, Federal University of Rio de Janeiro, University of Campinas, Uberlândia, the ABC in São Paulo, Santa Maria in the extreme south of Brazil. So, and I have also to mention, obviously, many students of our graduate program, and the teachers and professors like, for instance, Professor Angela Clautal, Jorge Castanheiras, Van Sérgio Alves, and professors, teachers from other institutions in Pará, and lots of teachers and professors and friends from all around Brazil, like I should mention some of them at least, Álvaro Nogueira, Luiz Cabral, Raimundo Santos, Roberto Hiroki, Rodrigo Capaz, and also people from very far away from Belém and Brazil now, like Professor Uli Eriksson and Borisov, as you have mentioned. So I should start with the questions. So the first questions that I have registered at the moment, Rodrigo, while I take control of the situation, why don't you turn on your microphone and please do your question. So Professor Rodrigo Capaz.
Thank you, Crispino. Thank you, Rosa, for your very nice talk. I have a question regarding the ruthenium trichloride graphene system. And it's actually a very simple question. I understand there is a mismatch between the two systems, yes, but the interaction between those should be very weak, should be van der Waals type of interaction. So yes, what is really the source of strain in the ruthenium trichloride?
Yeah, okay, so it's true. I mean, it's van der Waals, and what you see is basically charge transfer, but nevertheless, you still see that the point is that ruthenium trichloride is extremely sensitive to any small effect. So any small, even at the van der Waals level, you already can make changes into ruthenium trichloride. So the bonding in this system is extremely sensitive, and this, in fact, is giving also, it's affecting very much the interactions. So it's van der Waals charge transfer, and this is enough to introduce a little bit of strain into your system. Yeah, that's true.
Okay, so thank you, Rodrigo, for your question. Thank you, Professor Valentí, for your answer. Professor Van Sérgio from our university, Pará University, first, thanks you for the excellent and very didactic webinar. And he is mentioning that a recent work from himself and collaborators call it superconducting and pseudo-gap transition temperatures in high TC cup rates, and the TC dependence on pressure has been published, and they derived an analytical universal expression for the critical temperature and the pseudo gap in the cup rates and superconductors as a function of the doping. He mentioned that and asked if you can comment on that.
Yeah, that's very interesting. In fact, right now there is a lot of discussion about also the role of the pseudo. So it's very interesting that that you have done this work, because there is a lot of discussion about the role of the pseudo-gap phase and bad metal. And the more that you investigate these materials, the more phases that you put there. So that's I didn't know about this work, but it's certainly very interesting. If he got the relation between the TC and these different phases. Yeah, thank you.
Okay, thank you. So maybe one can write an email to you and you can start, talking about that later on. The next question I have here comes from Valber Hugo. Valber, do you want to turn on your microphone and make a question?
Yeah, can you hear me?
Yes.
Yeah, okay. Thank you very much for your talk, Professor Valentí. And I have a couple of questions regarding the P-wave superconductivity in this alpha ruthenium chlorium-3. And how does it compare with the P-wave phase in this strontium ruthenium oxygen-4? Because it also has a P-wave superconductivity, right?
Okay, so let me answer these questions in two parts. First of all, the P-wave superconductivity I'm talking about, and let me just maybe go to the slide. Here, there is no observation of that, okay? So basically what we did here is that if you take this model where you have these Kitaev and Heisenberg spin interactions and you add the hopping, basically you got this itinerancy, then there are different various groups, and this is a work from Ayard et al., where they calculated the phases that you would expect for different dopings. And this is all this set of phases: P wave, D wave, S wave, some are topologically non-trivial, others are. And basically what we did is we compared the parameters that we obtained from ab initio, where would we place in this phase diagram the material if one were to gate the material. So it would be in this region of P-wave superconductivity. So P-wave, as you understand it, a triplet superconductivity. But there is no realization of that yet. Now let me go to the strontium ruthenade, which you were mentioning. So strontium ruthenade, as you know, there have been in recent years a few experiments that, especially NMR, that showed that the initial NMR experiments that were done many years ago had a problem of hitting the sample, so that all this P-wave superconductivity that one thought that would be observed in this material, in fact, was not P-wave. It was because the system was still metallic. So this has been changing. And right now there is a lot of discussion about which is the nature of the order parameter in the strontium ruthenade. Of course, if you put this strontium ruthenade under pressure, you may change also the properties of this ordering parameter. I'm not in the field. I'm not working on strontium ruthenade, but I just wanted to mention that right now there is a lot of discussion about the order of the superconductivity. So which is the order parameter of in strontium ruthenade. Okay.
Okay, thank you very much. And just the last question, just the last one. Well, this strontium ruthenate oxygen-4, it's a kind of Hans metal, right? So it has some ortho differentiation and things like that. Mm-hmm. Well, have you explored this piece of physics in this ruthenium chlorium-3?
So wait a second. So you're talking about strontium ruthenate. Strontium ruthenate is a metal.
Yeah.
Okay. Ruthenium trichloride is an insulator. Now the Hund's coupling is in all these materials is important, and in fact this Kitaev physics I was talking about is there because of the Hund's coupling. So you need the Hund's coupling to realize this kita-F type of coupling. Now, going into the metals that I was showing to you, like the iron-based superconductors, there the Hund's coupling is also important as a metal because of the multi-orbital nature. So if I were to compare strontium ruthenium oxide, the material that has superconductivity, I would go more into the classes of itinerant materials I was talking about, not so much of ruthenium trichloride. I'm not sure whether I answered your question.
Yeah. Okay. Thank you very much.
Thank you.
Okay, thank you, Valber, for your question. Thank you, Professor Valentí, for your answer. Just to register, Valber Hugo is talking from Minas Gerais, I believe, so he belongs to the Federal University of Minas Gerais. So let's move to a question made from far away, but to our close friend, Ole Eriksson. Please go ahead, Professor.
So thank you very much for a very good talk, Roser. So this is a seminar series with a mixed audience, people from cosmology and solid state physics background. So I'm pretending now that I am a student in cosmology, maybe. Mm-hmm. So then I ask, I have two questions. Why do you talk about a quantum material? I thought all materials were quantum as long as you zoomed in at the short enough length scales and time scales, or length scales at least, on them. And isn't everything in the world quantum? And so why specify a quantum material? And my second question is, I thought the master equation for quantum physics is the Schrödinger or maybe the Dirac equation. Why do you come back all the time to the Hubbard, Hamiltonian, and Hubbard model?
Okay, so the first question, quantum, you're completely right. That's why I started with a piece of iron, basically to say, look, it depends on at which length scale we are describing the system. So at these microscopic length scales, all systems are quantum because it's interacting electrons. And the reason why I call it quantum all the time is because I'm working at the microscopic level. So I'm all the time working with electrons interacting, Schrödinger equations or Dirac equation. Now, your second question is, why on earth do I leave my Dirac equation or my Schrödinger equation and go to this effective model? And the reason for that is because I don't know how to treat correlations. So I don't know how to treat the Coulomb repulsion, this two-body interaction in the Schrödinger equation of many-body problem. So and I am interested only in the low energy physics of my system. So basically in what is really happening at energy levels which are around the Fermi level. And therefore, I can engineer a much simpler model that it only describes this low energy physics. So this energy window that is around the Fermi level. And such a model is the Hubbard model, which takes into account this Coulomb repulsion, doesn't carry with it all this complication of the full Schrödinger equation. And I'm limiting myself to a range of energies, which is about 1 electron volt from the Fermi level, which is the region of energies that is responsible for the transport properties of quantum materials. I don't know.
Thank
you
you
know that very well, but did I answer?
Then I have another maybe comment or question to you. There are other superconductors that, from a practical point of view, maybe are even more exciting than any one of the ones that you've been discussing now, and that is these high pressure phases of some hydrides. And so you want to make a comment on that also?
Yes. Yes, I can. Yes, thank you. Yes, so these are extremely interesting materials because these are, in fact, the superconductivity is well understood. It's in fact electron phonon, but we have to go to extremely large pressures to obtain this state. So this is, from a practical point of view, extremely impractical, since I need to go to, what was that, 100 gigapascals? I mean, really high pressures that we can only get them in the lab, or if we go in the so down into the earth. So that's why I need to look for other materials where I don't have to apply these very, very large pressures like in these hydrides. But they're extremely interesting because they have really high thesis.
Yeah, it is, of course, I agree with you, but it is actually quite exciting. So some of them are superconductors at the temperatures like -23 Celsius.
Yeah.
So a cold winter day, maybe not in Uppsala, but in the northern part of Sweden. So without any laboratory refrigeration techniques or so, you can have a material that out in the open would be a superconductor. Of course, the drawback is, it also says, you have to reach some 100 or 150 gigapascals, but nevertheless, it is actually, I find quite exciting.
I agree.
Yes. And those materials were predicted by theory, the kind of theory that Roser's been talking about before the materials were synthesized. And not only that, this class of with superconductors being relevant for in hydrides was predicted in Neil Ashcroft's thesis. You all know that they've taken solid state physics classes, Ashcroft and Mermin. So in his thesis, he discussed this, and so it's a cute story, I think.
It's a cute story. Yeah, it's the, as you say, is the really wonderful example of a prediction that then has been observed, and it's a clean prediction. I completely agree. Yes. Yeah.
Anyway, thank you very much, Rosa, for a very nice talk.
Thank you, Ole.
So thank you, Professor Eriksson, for your question. Thank you, Professor Valentí, for your answers. And now we have one maybe last question from Angela Clautal. Angela, please.
Hi, Roses. Thank you a lot for your talk. It was really good, interesting. I would like to ask you if you can comment about the studies using machine learning that you know about this subject. Could you please?
Yeah. So we have been we ourselves have been looking into two directions. So one is, I was showing to you that if we are interested in correlated materials, we need to do, on top of these DFT calculations, we need to do many-body type of treatment, like dynamical mean field theory, variational Monte Carlo. So what we are doing now is, and these type of calculations are can be rather elaborate, and also the accuracy, you have to be very careful about the accuracy, for instance, in dynamical mean field theory. So what we have been doing recently is putting machine learning or using machine learning ideas in order to improve on these calculations, to make them more effective without having to do the whole calculation every time. So this is one direction. The other direction is by using these methods to predict directly phases. So especially we were interested in topological phases. For instance, I was showing to you all the time these kinetic hopping parameters. So what we have been doing recently is, if you have a bunch of hopping parameters that could represent any material, so basically depending on the hybridization that you have there, whether you could, out of that, by using machine learning ideas, or basically the machine learning process, whether you could then predict the certain type of topological properties. So basically, I would like, for instance, to have an insulator with Chern number 1 or with Chern number -1. So this is, in fact, a very useful direction also to apply machine learning. And the third one, which we are not doing, but other groups are doing, is directly to do, in fact, the search for materials directly by applying the machine learning algorithms. But these I haven't touched that much. But what I want to say is that these kind of algorithms help a lot to fasten your calculations. So that's, and you can even reach regimes that you wouldn't maybe find by the normal calculation that we have been doing for the last years. So that's why I think it's very exciting to use these methods.
Oh yeah, thank you very much.
Thank you.
So thank you, Professor Claude, for your question. Thank you, Professor Valentí, for your answers. And to finish our session, I would like to ask everybody to turn on their microphones once again and to give a huge applause in retribution for this wonderful webinar. Thank you very much, Rosa.